Okay, good afternoon, everyone. So we'll continue with this case which we had started yesterday. This was the case where one end was fixed or clamped and the other end was pinned. And we had taken up the differential equation, and we had first of all started with the second order differential equation version, and then differentiating twice we had obtained the fourth order differential equation. And then what we did was to use four different boundary conditions. So the conditions that we used, so if you remember, at x equal to L, where L is the length, at x equal to L, you had y is equal to 0 and dy dx equal to 0. At x equal to 0, you had y equal to 0 and m equal to 0. So using all those four conditions, ultimately we arrived at this condition. Okay, this tan KL equal to KL. So I had asked you to try it. Did you try? What is the approximate value of KL for which this would be true? 4.4. Did you manage to do it in your calculator? Okay, good. Okay, so because that is what you would actually require. So KL, it is approximately 4.49. Okay, we'll call this as 4.5 approximately. Now this being this value, so earlier, please remember, guys, please settle down. Akshat. So earlier, if you remember, for the pinned case, we had obtained sine KL equal to 0 and KL had turned out to be equal to n pi. Okay, so we are in a similar situation now. Okay, now of course, please note that there it was n pi, and consistent with our expectation, 4.49 is the first value which would satisfy this. It does not mean that you will not have other values also. You will have higher values also. Okay, but this is the smallest value for which this is satisfied. Well, smallest value is scale equal to 0, but that's a trivial case. All right. Now, K, we will say that from now on we'll use equal to in proper engineering spirit, and we'll also call this as 4.5. Okay, divided by L. And we want a square because this K square is equal to P by EI. Now see, it has started to look like what we had obtained earlier. In the pinned case, if you remember, or if you don't remember, you can go back and check your notes. We had obtained pi square EI by L square. Okay, pi square EI by L square. And later for the other cases, what we had tried to find out was this value of P, this critical value of P in that particular form itself, the pi square EI by L square form. It is no longer in that form. So we'll make it in that form. So what we'll do is just a little bit of algebraic adjustment. So in the numerator I have multiplied by pi square. In the denominator also I need to multiply by pi square. I also need to take the 4.5 square downstairs. Okay. So overall what this will become is this. Okay, and this thing pi L divided by 4.5, that is the effective length. Okay, so please check what is this value, pi divided by 4.5. To the first decimal place correct, 0.7. Okay, 0.7L. That's all that we are interested in. So the effective length for this case, where you have one end fixed and the other end pinned, is 0.7 L. Please try to remember these effective lengths, at least for these types of very typical cases. Okay, for each and every case, you can always find out an effective length, but these are the very typical cases. The pinned, which is the absolutely fundamental case. Then you have the fixed free, then the fixed pinned. You'll also have a fixed case. Okay, but we'll not do it in class. All right. Uh, till now, if you have any issues or if you have any questions, please do ask. This particular case is over. Okay. All right. So we'll move on. As I just mentioned, we'll have another case where the bottom end is fixed and the top end will also be fixed. Okay. And in that case, you will also find out a certain value of the effective length. Okay. So you do that yourself. I think there is a problem like that in the tutorial sheet. Anyway, we'll now move on to a very important discussion, very easy maths, but a very important piece of discussion. You please note that again, let me go back to my ruler if I have it. Yes. So please note that this is like a column, right? Now, yesterday I had demonstrated that if I press down on it, what happens? It bends like this. Okay, it bends like this. Now, do you expect that if I press down on it, I will manage to make it buckle in this way, this sideways? So maybe take a look like this, and maybe I stand in front of the camera. Okay, so if I do like this, if I hold the thin edge normal to you, then if I hold it like this, then it buckles. But no matter what I do, I will not be able to trigger the buckling in that other plane. Okay, why do you think that is? It is only to do with the I. Okay, the second moment of area. You look at that thing, this pi square EI by L effective square. This is the general form that we have found out for P critical, pi square EI by L effective square. So as you are increasing the value of this P, the moment it hits the P critical, you will expect the buckling to occur. Now, this I will have different values depending on the cross section and depending on the axis about which you are calculating the I. For the ruler, the I about one axis is significantly lower than the I compared to the other axis. Okay, which is why at least for a rectangular cross section you will have a I minimum and a I maximum. In fact, you can always find a I minimum for a cross section. Okay, so this is very important. So when we write this thing, we intuitively understand it, but when you do the maths, it is very important to note carefully that this is actually the I minimum. And you will see a number of problems in your tutorial sheet actually distribute. Karthik. So please distribute. So if you look at the tutorial sheet, you'll find a number of problems where this difference in the I has to be carefully taken care of. Okay, all right. Now we want to do something special with this. We have the P critical. Now, what we'll do is we will try to look at this. We'll try to reconsider this not in terms of the force, but in terms of the stresses induced. So what do we need? Well, of course, it has to be the average stress. So we will divide this P critical by the area of the cross section. Very simple algebra. So P critical divided by A. So this thing is the sigma critical. Okay, this is the sigma critical. Now if we have that, what we can write is this I minimum, we can again rewrite it in terms of the radius of gyration, because you know that when we write in terms of the radius of gyration, the area of the cross section comes into the picture. Okay, so keeping everything else same, we'll just write this as A times R square. All right, where this R is the radius of gyration. So you see very nicely this A cancels out from the numerator and the denominator, and what we are left with is this thing. Pi square E divided by L effective by R whole square. Now just take a quick look at it and tell me whether it seems dimensionally correct or not. On the left hand side you have a stress, which is Newton per meter square or Pascal. On the right hand side pi, no unit. E has the unit of Pascal, and in the denominator you have a length divided by another length. The radius is after all another length. So everything is nice and consistent, at least in terms of the units. Now what is this L effective by R? So see this R, the radius of gyration for a rectangular cross section, you actually do not have any radius, right? But this is like the radius of gyration is like the effective radius. Okay, so this L effective by R, it denotes what is actually referred to as the slenderness ratio. Slenderness ratio means, try to think of it like this. If you did not know any maths, if you did not know any mechanics, okay, and I asked you that whether this thing is slender or not. Slender means whether it is thin or not. What would you say? Yes. So as a human being functioning in this world, you have an intuitive feel of what is thin and what is not. Okay. And when you are gauging your friends, the closer your friends are, the more skewed your perception will be. I will not dwell on that anymore. What do you think about this? Is this slender? Now you're not very sure. Okay. Well, it seems slender, but the thing is, I will not be able to buckle it, right? I'll not be able to buckle it, no matter how hard I press down on it. The reason is that it has a very high stiffness. Okay. So slenderness ratio has an important role to play in buckling, but so does the stiffness. The stiffness is given by that E. Okay. So overall, that is the picture. You have that factor pi square, but that is just a number. The real thing is that stiffness, but together with the slenderness ratio. Higher the stiffness, higher will be the value of the P critical. Okay. And higher the value of the slenderness ratio, what will be it? Lower. Okay. On the left hand side will be lower. So this relationship between the slenderness ratio and the stress, it can be very beautifully plotted out, and it looks somewhat like this. So It looks like this. Okay, very fast decaying, but don't call it exponential decay because it is not. Okay, looks like that, but it's not. Now, who can tell me what is the catch in this diagram? So let me just tell you. By the way, this thing is horribly not straight. Okay, so what we are saying is this L effective by R, the higher it is, the lower is the sigma. But the lower it is, the higher is the sigma. Does this region make sense? See, when we are thinking in terms of mechanics and we are thinking only in terms of one chapter, this kind of picture is good. But when you are out in the field, in the professional world, then Mother Nature doesn't care which chapter you are more, which is your most favorite chapter. Okay, so everything takes place all together, and you have to keep your eyes and ears open. So tell me that is it possible for a specimen to have this infinitely high kind of stress? What happens if the stresses start becoming too large? Plastic yielding will occur, if not anything else, right? So if you have a ductile material and you have the stresses rising sharply like that, so you will encounter a point where the material starts to yield. So now you have to take into consideration two things. On the one hand, you have buckling failure, and the other you have plastic failure, okay, or plastic yielding. So suppose that our yield value is somewhere here, sigma y. So you have to draw this kind of a horizontal line, and you have to very carefully think it out that the real failure line will be like this. This is not the one. Okay, this is just a theoretical thing which you can plot out in MATLAB or Python. But in reality, the moment you hit this, it'll flatten out like this. This is the thing. Of course, in reality, if you carry out experiments, you will never get these kinds of sharp corners and things like this. We'll have a scatter of points, but we'll study those kinds of things in more detail in the design of machine elements course. Okay, but this is a very simple thing. Okay, very simple thing, but it's of immense importance. When we ask you to do a problem, and maybe we ask you to investigate failure, if you just investigate the buckling thing without caring about the plastic thing, you may be in a very dangerous situation. Okay, so please remember this. All right, so first of all, just to recap, remember that this is the I minimum. This is extremely important. Okay.
Scale, can you show where which direction is the eye is? For the scale right and not right?
This one, because this I, so if I take the axis, so let's hold it like this. Okay, if I take an axis like this, then the I will be like this, about this thing. Yeah, so it becomes very high. Okay, but if you take an axis which is like this, so you see there is barely any material above and below the axis. So the formula is 1 by 12 bh cube, right? The h cube is there, but that h cube is barely contributing anything because there is hardly within that 1 millimeter. I mean, it's like 0.5 above and below the axis. That's why.
So,
Yes.
wouldn't that I actually depend on the axis along which the force P is applied? Because if it is
No, these forces. So what Akshat is asking is that wouldn't it matter along which direction the force P is applied? For our cases, we are always considering the P to be a centric loading.
so not the direction of the force, but the distance.
Location, right? Location, right? Location. Direction is always downward, like into the axis. But what I'm saying is that in addition to it being into the axis, the P is also centric. Okay, which does not mean that you will not have buckling if it is not centric. Of course, you are going to have buckling. Okay, but we are not going to consider that situation. That topic is absolutely out of the syllabus.
So along the neutral axis.
Sorry?
Along the neutral axis.
So see, the situation is something like this, that if you have a cross section which is like this, okay, this is the center. All our cases will be like this, where it is through the center. But suppose you have a force like this, okay, then in addition to the axial loading, you are also going to end up with a non-zero bending moment. So it is a simultaneous case of an axial load and a bending moment. The way to address those things is a little bit different. It can be done. If you're really interested, you can take a look in Beer and Johnson. They have done it, but not in very much proper detail. Okay, so that's it. Now, of course, as a precursor to what you would be doing in your sixth semester, let me tell you something very, very important. In your sixth semester, you're going to do an lab. I think it's called the engineering mechanics lab or the applied mechanics lab, something like that. Okay, so that's the first time in the history that we are going to have that lab because you are the first batch. Okay, it is the successor of the mechanics of solids lab which you used to have earlier. Okay, but new experiments are there. Now we are going to incorporate the buckling experiment there for the first time. Your batch will be the first batch to do the buckling experiment. Now the thing is that in reality capturing this P critical experimentally is extremely difficult. So maths is okay, but capturing it experimentally is very difficult. So we go about doing it in a very indirect way. That method is a very classical method, uh, first found out, I think, in the early decades of the 20th century by somebody called Southwell. Okay, so it is referred to as the Southwell plot method. You don't have to do it right now. Okay, so we'll study that later on, the Southwell plot method. Okay, so you again solve differential equations, but ultimately you arrive at something which will be actually experimentally useful. Okay, so the lesson that I want to convey to you is this: there is something called mathematical precision. Okay, there is something called differential equations, and all that is good and fine. But ultimately, when you have to measure something, then you have to incorporate all your knowledge of maths, physics, chemistry, everything together to be able to do something which you can actually practically measure. Because unless you can measure something, how can you even do the experiment? Okay, so when you do the experiment in your sixth semester, do the experiments in your sixth semester, you will see that there is a little bit of a gap between the theory and the experiment. Okay, which is why we have kept it in the sixth semester. Earlier, this used to happen in the third semester itself. Now, students did not have the mental maturity to appreciate what was really going on. So we thought that okay, let the students first learn the theory properly. You will have learned design of machine elements also. So the second semester of your third year, maybe the hope is that you will have more maturity to appreciate what is going on. Okay, so we'll cross that bridge when we come to it. Okay, now you have all seen you have all gotten the tutorial sheet. If you have some extra sheets, please give it to Shamrat, who is sitting at the back. Okay, and give me one sheet, Shamrat. Thank you. Yes, you also want one sheet. Okay. So all of you take a look at question number 3. Tutorial sheet 5, question number 3. The uniform brass bar AB has a rectangular cross section and is supported by pins and brackets as shown. Each end of the bar can rotate freely about a horizontal axis through the pin, but rotation about a vertical axis is prevented by the brackets. Determine the ratio B by D for which the factor of safety is the same about the horizontal and vertical axis. And then you have to do a calculation. Okay. So I will try to draw a rough sketch of this figure. Now see, it is pinned here. Okay, so it is pinned here, it is pinned here. But the pins have to pass through certain brackets. The presence of those brackets, I'm not drawing it here, okay? So please understand that over here, and over here, you have some brackets, okay? Now the presence of those brackets at this end, they will prevent the free rotation at these two ends like this. So if you have something like this, so let's say that this is your thing, okay? So it is free to rotate in this plane, okay? It is free to rotate in this plane. But at these two ends, it is not free to rotate like this, okay? So it is kind of fixed. If the picture is not clear to your mind, please let me know. Okay. Now, what do we have to do actually? See, the question is that determine the ratio B by D. Now, B is this dimension. This is the dimension B, and this is the dimension D. So we have to determine the ratio B by D for which the factor of safety is the same about the horizontal and the vertical axis. So basically, the thing boils down to the consideration of buckling in the two different planes. And this is something which you will have to repeatedly do in many of the problems. This is a very, very standard problem scenario. You have two different planes in which buckling could possibly occur. You have to test it out and find some condition. So what do we do? First of all, we note that the two end conditions are different for the two buckling, for the two cases of buckling. Okay, so case 1, this is the pinned case. Right, this is the pinned case. Now for this, what is the value of I1? Tell me. One by 12? Is it BD cube or is it DB cube? See, when we are considering this thing, the buckling like this, so we are expecting this thing to buckle like this. Okay. Okay. This is an exaggerated diagram. Okay. So this is the thing. So our cross section, which is the cross section of interest here? Of course, it's a rectangle. Okay, rectangular cross section is both ways, but about which axis we are doing this thing? Horizontal is come on. Achha, let us make it nice and clear. Let's say that this is the x-axis. Let's say this is the y-axis, and let's say this is the z-axis. Okay. So when we are considering the buckling like this, okay, the buckling like this, like what is the plane along which the neutral axis for that thing is parallel? Is it the xz plane or is it the yz plane? YZ. Why is it?
CSA is along that way.
So tell me one thing, that suppose you have a beam like this. Okay, suppose you have a beam like this. Okay, you have a beam like this. We have the x-axis like this, we have the y-axis like this, and the z is coming out. Okay, and this thing is bending like this. This is our usual case which we have been doing time and again. Okay, so here the cross section is something like this, is it not? Okay, this is the thing. So the axis about which this is happening is this axis. Okay, this is the axis, and this is the height, and this is the breadth. Is it not? Then what is the height? So here, this is the height, this is the breadth. What is the height here? D. So shouldn't it be BD cube? Okay. Case 2, this is the fixed case. Here, this I2 will be 1 by 12 dB cube. Okay. The L effective here will be what? L. And the L effective here will be what? Well, we have not done the case, but it is going to be 0.5 L. Okay. This is 0.5 L. So if you do not trust me, you can look at question number 10. Look at question number 10. So for a column with clamped conditions, the critical load may be determined by solving, and I've given you various kinds of instructions which what to follow and how to go about doing the problem. And look at the ultimate answer. It is pi square EI divided by 0.5 L square. Okay, 0.5 L whole square. So the L effective is indeed 0.5 L. Okay. So here I am writing this as refer question 10. Okay, we have this much information. Now very quickly we can solve this problem. So it has been said that the factor of safety has to be the same for a given load. Now, you know that for factor of safety, you have to divide one force by another force. Now you tell me which force by which force. Or for factor of safety, sometimes you have to divide some stress by some other stress. Here it is in terms of forces. So you tell me which force by which force. Critical by the given force. Okay. So factor of safety, that will be P critical divided by P. What is the justification behind this? See, if you hit the P critical, you are already buckling. But if you give a certain value of P, the load, which is less than this P critical, you have a margin between the applied load and the P critical. Okay, so this P critical by P, that is the factor of safety literally. Okay, so this P critical by P has to be the same for the case 1 and the case 2. Okay, now this P is the applied load, that is the same in both the cases. So the only difference is this P critical. Okay, so if we have to write this, that factor of safety for case 1 is equal to the factor of safety in the case 2, it ultimately boils down to the P is the same. Okay. So ultimately it boils down to P critical 1 is equal to P critical 2. Now P critical 1, we have already seen here what are the things. So pi square E I1 divided by L effective 1, and this is pi square E I2 divided by L effective 2. So please do the algebra quickly. E is the same for both the cases, okay? Young's modulus is the same. Yes. Yes. Sorry? For the this one, second one. So here the fixed phase case is what? Here we are considering the buckling to be like this. So imagine that this is the thing, okay? And now we are considering the buckling in this out of the plane board. So we are considering this one. Okay, this one. That's why. So here when you are considering it, this thing at the two ends, this is fixed. Okay. And if you have, so again look at this diagram. So when it was bending in this direction, then this was our neutral axis. Okay. But when it is bending in this direction like this, so if it is bending like this, then the neutral axis will be this one. Okay. The vertical one is the neutral axis. Okay. So here it is clearly mentioned, right, that each end of the bar can rotate freely about a horizontal axis through the pin. The pin is there, but rotation about a vertical axis is prevented by the brackets. Okay, so the brackets, they prevent the rotation. Okay, prevent the rotation means it's like a clamped or a fixed end. So are you getting the answer here? Okay, so B is equal to how much? 0.5 D, right? I think that's the answer, right? So B is equal to 0.5 D. Now once you have obtained that, the second part of the problem I'm not going to do. You just plug in the values, you'll get it. Okay, the second part of the question is asking us that determine the factor of safety if P is equal to 8 kilonewton. Okay, so all that you have to do, so from this, first of all, you obtain that B is equal to 0.5 D. Okay, this I believe most of you have obtained. After you have done that, in order to find the factor of safety, this is what you have to do. Okay, divided by P. Divided by P. This P is this is the 8 kilonewton it is given. Okay, this is the 8 kilonewton. Young's modulus is given, I1 you know, but in case some of you are thinking that what about I took the case 2, then also it would have been the same, because you've already ensured that the factor of safety is going to be the same. Okay, so it is perfectly equivalent if you want to take up the case 2. You can check for yourself. It will come out exactly the same. All right. Next, let's consider this question number 4 itself. Yes.
When a sufficient load is applied in this direction, will let occur.
So, if you just take a rectangular cross section, okay, and you have the ends just pinned, then it is always going to buckle in such a fashion that the I minimum is the one which is activated. That is all that you have to remember. Okay, the other one will not even buckle. The other direction will not even buckle. Okay, which is why we use the I minimum thing. Okay. Okay. Question number 4. So this so this hatched part, that is our column. Okay. Now this column has been set up in a very special way so that different parts of it are under different conditions. Please note that at the bottom there is a pinned end and the top there is a free end. Now here and here, what do you have? Well, these are like vertical guides or guided supports. They do not prevent the movement in this vertical direction, but they prevent the rotation. Okay, they prevent the rotation like this. They prevent the rotation like this. Prevent the rotation means what? It is a clamped end or a fixed end. Okay, so let me just. So this is A, this is B, this is C, this is D. And we'll consider the different parts separately. The question which has been asked is that, well, first of all, it has been given to us that LAB, the length of the part AB is 1.4 meters. And what we have to find out are the largest possible values of the part BC, that is the LBC, and the largest possible value of this part CD or the length CD, LCD. Okay. So what is the like the absolutely critical condition when you are applying a load? What is the condition? Like physically, what do you expect? Like it is just about to buckle everywhere. Is it not? It is just about to buckle everywhere. Now, just about to buckle everywhere means what? So you have increased your P to such an extent that all these three parts, like you consider although they are all connected, part of the same member, but because of these supports, you consider that AB is one member, BC is another member, and CD is another member. Now these different parts, they can individually buckle. The force P will be such that they are all about to buckle. Okay, they are all about to buckle. Yes, all at the same time.
They require different feedback.
Sorry?
Every part of them require different feedback.
No, because see, they are actually part of the same P, right? So no matter which cut section you take, the P will be the same.
But required critical field is
Sorry?
critical field.
Critical P will be different. Okay, critical P will be different if you take if you take the same lengths. Okay, that is what we have to do. Okay, if you consider the same length, okay, suppose this is 1.4, this is 1.4, this is 1.4, certainly the P critical will be different. But that independence has been given to us, that you choose the L at what all of them will be in the dangerous situation. Okay, that is the question. Okay.
Why all should buckle at the same time?
What do you want?
So like even if one section buckles, that will render the whole column useless.
No. Okay, so now we are, doing jhagra over the semantics of it. So one can argue that maximum possible lengths of BC and CD are given. Okay, I will take BC to be 1 kilometer and CD to be 1 kilometer. Or maybe the other way around. Maybe I'll make it very small, 1 millimeter and 1 millimeter. Okay, doesn't matter. As long as this AB thing buckles, I will say the whole thing has failed. Okay, but that is not what is meant. Okay, so bhavnaon ko samjho. So you tell me, what do I do? Is a simple thing actually. Okay, so we just have to ensure that all of them are buckling at the same time. Now all of them buckling at the same time means what? That you have this P thing, and this P thing will be equal to the pi square EI divided by the L effective square, right? L effective square. Now for the different parts, you'll have different L effective. Just write that. I mean, that really is as simple as that. So in one shot I will write it. Okay, so for the part AB, okay, for the part AB, you tell me what is it. This is pinned and this is fixed. For BC, what is it? Both are fixed. So this L effective for the pinned fixed case is what? This is the first thing that we did today. Yes, 0.7 L. Fixed. Right. This is 0.5 L. Exactly. So we have to write this as LAB. We have to write this as LBC. And for CD, this will be fixed free. Go back to your notes and tell me what was the L effective for fixed free. It was twice L. So it will be twice of LCD. That's it. So all that we have to do here is write this as 0.7 LAB whole square. This is equal to pi square EI divided by 0.5 LBC whole square, and this is equal to pi square EI divided by twice LCD whole square. Okay, so what you have basically is that LBC is equal to 0.7 divided by 0.5 LAB and LCD is equal to 0.7 divided by 2 LAB. You know LAB is equal to 1.4 meters. We get the answer. Yes.
Buffering can happen out of the plate, right? Why is it not happening out of the
So, in question number 4, the second last line you see, consider only buckling in the plane of the figure. Okay, you take a 5-minute break.